At this point, we've gone through the process of selecting a model, selecting a loss function, and minimizing average loss across our entire dataset in order to determine optimal model parameters. And by doing that, what we are doing is fitting our model to our data. Now that we've fit our model, let's look at a few ways that we can determine if our model is any good. So there are 3 techniques for evaluating models that I wanted to mention today. The 2 that I wanted to look at today are the root mean squared error and some measure of correlation, and we'll get into the specifics of what I mean shortly. The one technique that we won't discuss today is looking at a residual plot. Now, a residual is defined as being the difference between an actual y value and a predicted y value. It's how wrong our prediction was for a single observation. There will be an entire section of the next lecture dedicated to residuals, their properties, and residual plots. So we will save all discussion of residuals until next time. So let's start off by looking at the root mean squared error. The root mean squared error is defined as being the square root of the mean squared difference between predicted values and their true values. This might sound familiar, and it's because the root mean squared error is just the square root of our good friend, the mean squared error, which has been the average loss that we've been minimizing to determine optimal model parameters, at least when we choose our loss function to be squared loss, which is what we've done throughout this lecture. The reason we take this square root of the mean squared error is because the units of the root mean squared error are the same as the units of our y. So if, for instance, our x is measured in inches and our y is measured in pounds, the units of the mean squared error are pounds squared, but the units of the root mean squared error are just pounds. So it makes things a little more interpretable. Now, our goal when fitting our model to our data was to find the model parameters that minimized mean squared error. So that means low values of mean squared error, and consequently root mean squared error, mean that our model makes more accurate predictions. So when it comes to comparing models, we say a model that has a lower root mean squared error makes more accurate predictions. Now, one issue with root mean squared error is that it's an absolute metric and not a relative one. What I mean by that is there's no bound or predefined range that a root mean squared error has to fall into, right? Root mean squared error could be 2, it could be 100, it could be 10,000, and so it's not as easily interpretable as, say, a correlation coefficient. One nice benchmark or baseline to look at for the root mean squared error is to compare our model to the constant model. Now, you may remember when we chose our loss function to be squared loss, the optimal model parameter for the constant model was the mean of our observations, and the mean squared error when we used the optimal model, so the mean squared error when we used the mean, was the variance of our observations. That means the root mean squared error of the optimal constant model was the standard deviation of our observations. So we would hope that the root mean squared error of our simple linear regression model or multiple regression model is lower than the standard deviation of our observations. Because if it's not lower than that, then our model is worse than the constant model, which is about as simple as we could get. Now, one thing to note is that using the data that we have available to us, as we add more features, our root mean squared error will never go up. And this is because if we add on a new feature that doesn't help reduce mean squared error on our data set, the optimal model parameter for that feature may be very close to 0 or actually equal to 0. So adding more features never hurts us when we are evaluating mean squared error on the data set that we are training our model on. But soon we will start evaluating our model on data sets that we didn't use to train it. And in those situations, it's no longer the case that adding more features can't make our model worse. In general, adding more features could be a good thing or could be a bad thing when it comes to the generalizability of our model. And we will talk more about that in a few lectures from now, but I just wanted to get you thinking about this idea that adding more features doesn't necessarily make our model better, even though the root mean squared error might be lower on the data set that we've collected. Soon we will start discussing terms like training error and testing error of our models, and when we do that, root mean squared error is often the error that we will be looking at. Now, to look at a tangible example, let's go back to the two linear models that we were discussing in the previous video. We have one where we are using assists to predict points per game, and another where we are using assists and 3-point attempts to predict points per game. In this scenario, the model that only uses assists has a root mean squared error of 4.29 on the NBA dataset, and the model that uses assists and 3-point attempts has a root mean squared error of 3.64. So you can see here, we added a feature and our root mean squared error decreased, which makes sense because we only have one data set for now. And as I just mentioned, if we are evaluating root mean squared error on the same data set that we use to build our model, it will never go down as we add more features. But in this case, it seems like adding 3-point assists as a feature made our model make more accurate predictions. Now let's look at some measures of correlation. Back when we had just one feature x, we were able to look at the correlation coefficient r between our x and y to get a sense of the strength of the linear association between x and y. The issue we have now is that we don't have just one independent variable or just one feature x. Now, with the multiple linear regression model, we can have any number of features. And so one thing we could do is look at the correlations between our features themselves individually with our y values. And that is something that you may do in practice, actually. But what we're more concerned about is looking at the correlation between our actual y values and our predicted y values. We want our predicted y values to be as close to the actual y values as possible, and so we want the relationship between actual y values and predicted y values to be as close to the identity line y is equal to x as possible. We want them to sort of be very strongly positively correlated with one another, which indicates that our predictions are quite close to their true values. And so the multiple r squared value or multiple r squared coefficient is the square of the correlation between our true y values and predicted y values. So in here, we have r for correlation coefficient of y and y hat, actual y's and predicted y's, and we're squaring this. The reason we are squaring this correlation is sort of outside of the scope of this class. It has to do with ideas like total sum of squares and explained sum of squares if you're familiar with those terms. But for us, let's just take it at face value. This is the definition of the multiple r squared value. And since it's the square of a correlation coefficient, which ranged from -1 to 1, it ranges from 0 to 1. An equivalent way of expressing the multiple r squared value for linear models that have an intercept term is this. We can write it as the variance of our fitted values divided by the variance of our y. Now, fitted values, this is a new term. This is just another term for our predicted y values. It's just something that you should be aware of, fitted values. Another way of sort of writing this symbolically is as sigma squared of y hat divided by sigma squared of y. And the way we can sort of interpret this is as being the proportion of variance in our sort of true y values that our model is able to capture or explain. So you can think of the r squared value as being a proportion of variance that we are able to explain using our model. Now, just as when we looked at root mean squared error, it's important to note here that as we add more features to our model, our fitted values or our predictions tend to become closer and closer to our actual y values. And so the r squared value tends to increase. In the case of our NBA models, the simple linear regression model that just used assists had an r squared value of 0.457, meaning that it was only able to explain 45.7% of the variation in the true points values. The model that used assists and 3-point attempts was able to explain 60.9% of the variation in the true points values. Now, I didn't explicitly mention this, but both these multiple r squared values and these root mean squared error values are things that you can calculate using the supplemental notebook that's provided with this lecture. Now, once again, it's important for me to bring up that adding more features to your model doesn't necessarily make it better. Once again, we are a few lectures away from understanding why. To get a taste of where we were going, for instance, if we add features like, does the player like ketchup? How many days old is the player's mother or father? If we start adding features that have nothing to do with our data, even though the R² value may go up slightly or our root mean squared error might go down slightly, when we start evaluating our model on data that we didn't use to create it, our model will have some wacky predictions. But again, that will be the subject of its own lecture, and I just wanted to give you an idea of where we are going here. The adjusted R² coefficient accounts for the fact that adding more features doesn't necessarily make your model more robust, but that is way outside of the scope of this class. It's just something I wanted you to be aware of. Let's take a few minutes to wrap up and summarize all of the ideas that we've looked at today. So we now know about 3 models. We know the constant model that just makes predictions using a single constant theta. We know the simple linear regression model, and we also know the multiple linear regression model. Each of these we've now expressed as being some function f of an input value x parameterized by our choice of theta. And if we are using the optimal model parameters, we call this f theta hat of x. We studied the correlation coefficient and looked at its properties. We by hand derived the optimal model parameters for the simple linear regression model, which again we saw in data 8. We also talked about this idea of a feature and how we aren't restricted to just having a single input variable in our models. We wrapped up by talking about root mean squared error and the multiple R² coefficient as ways of evaluating the quality of our models that aren't restricted to just having a single input variable. Next time, we will sort of formalize a lot of the things we saw in this lecture. We will express the multiple linear regression model using matrix vector notation. We will explicitly solve for the optimal model parameters for the multiple regression case, which we sort of abstracted away in today's lecture. This will involve quite a bit of linear algebra, so just make sure you're ready for that. We will also spend some time talking about residuals and their properties, and in that lecture we will wrap up by thinking about what it means for a model to be a linear model. That's it for today.